Hey, welcome back, everyone. We'll have Andrea again continue his Turing lectures.
Okay. Okay, thanks a lot, Pratik. Thanks for everybody for showing up despite the first lecture. Okay, so as promised today, I'll try to go into a little bit more in technical depth into the linear theory for overparametrization and generalization in overparametrized models. So the theory that applies to the neural tangent regime, and then tomorrow I'll talk about more dynamical or feature learning view of it and more recent work. So this is work that was done mostly a few years ago in collaboration with a group of then PhD students, Beruz Gorbani, who is now at OpenAI, Song, who is now in Berkeley, Tio, who is now in Yale, and Yi Chao was a postdoc, who is now in Wisconsin. And okay, I'll try to highlight work with Chen Cheng, who recently graduated. Okay, so I remind you from yesterday, I erased the title here, but this experiment, I showed several versions of this experiment in which, again, you fit a two layers network. In this case, this was from this paper of Misha Belkin, Daniel Shu, Sumik Ma, and Mandala, and then you increase the number of parameters, the weight, the width of the network, and you plot test and train error at convergence, and you see this double descent phenomenon if you don't regularize, and then there is this decrease of the training error, there is this interpolation threshold, and the peak of the test error is at the interpolation threshold. Most important part of, I think, these plots is the fact that you got good test error despite a big gap here in the highly overparametrized regime. So that is really statistically the most important feature of this plot. Now there is one bit of information that if everything else gets lost is that this phenomenon is completely general. It's embarrassingly general, and this, in my opinion, is the simplest model in which you can demonstrate it. And this is so simple that everybody should teach this to undergraduate students. Right? The model is just the following: you take covariates, it's a toy model. You take covariates that are normal 0i, and then a response that depends on these covariates, right? Theta times xi plus noise. And then you compute some feature vectors, right? But the feature vectors are computed in a very simple way. They are just a matrix times the xi plus noise. So these are noisy, normally featurization maps are nonlinear. This is a noisy linear featurization map, okay? And we think of P as larger than D, as often is the case, right? So there is an underlying low dimensional structure to the model, that is this one. But of course, if you fit to the data, but if you fit a model to it, you fit it to higher dimensional features that don't correspond to the reality. They are some noisy function of the reality. Now, the nice thing about this model is that I can increase the number of parameters without changing the underlying dimension. So it's a linear model. There is an underlying latent structure, and the number of parameters can scale independently of the dimension. And now what I'll do is that I'll just regress y on z. And if I do this, now I plot this versus P over n. So this is number of parameters versus number of observation. And this is what I observe. And the curves are theoretical predictions for different sample sizes. This is theoretical predictions, and the dots are simulations. Here, notice there are three-dimensional parameters. I mean, two-dimensional parameters D and P, and then there is n that is the sample size. So here, these three plots, I don't remember what is d, but these three, I think d is 100, but these three differ in the ratio of n over d. Okay. So you see the same, kind of qualitative feature as before, and then you can explore all sorts of phenomena here. For instance, here we plot the same curves for different values of the regularization parameters. And the interesting fact here is that if you choose the regularization parameter optimally, you, remove completely this spike here. You get, a decreasing curve, monotonically decreasing curve, which is nice, and is what you should expect. So if you regularize well, more data always help, at least in this model. And the other interesting fact is down here that the unregularized curve, so the lambda equals 0 curve is the optimal one. Lambda equals 0 really means lambda 0 plus, so minimum norm. Okay? So these are the two interesting facts. It's the same fact that we observe, people observe empirically, and you can really teach them to undergraduates. An equivalent way, of course, to think about, since everything is Gaussian here, I can eliminate the latent variable and view everything, write the relation between y and x, but y and z, you can write it directly as y equal beta zi plus, some other noise, and then the zi now will have a special structure that comes because these are w times xi plus Gaussian noise. So in particular, if w is skinny, the covariance of the z, you see, it's an identity component that comes from G plus W transpose, right? So, the covariance structure is basically identity plus low rank. And, the real, feature of this is that this is a covariance that has, a latent low dimensional structure. Or in other words, the eigenvalues of the covariance have some big values and then many small values. And then if you compute what is the beta in this coordinate, beta belongs to the span of W. So this is a linear model in which, another way to think about it is a linear model in which the covariates have, are anisotropic. So they have, they basically are nearly aligned with the low dimensional subspace. And the real coefficient vector, the true coefficient vector, is aligned with the same subspace, right? So there are lots of spurious dimensions that are, junk covariates, junk dimension. They simply are in there because, you construct your features when you do any machine learning model, and a lot of the features that you construct are irrelevant in one basis or another. Yes? This is test error. Yeah, thank you. A test error here, everything is square loss. Yeah, so here, at least if you look at it, is, if I look at very large gamma, if I fix gamma, then, another regularization parameter is optimal. But if I look at very large gamma, then 0 is optimal. Now, it's not always the case. And yeah, I don't remember if I have a slide about that, but perhaps, remind me. Yeah, there is a slide on which I can explain this a little bit more in detail. There is a way to understand this. This is this spike. Well, all of these curves, the continuous curves, are all analytical formulas. They are, a few lines of formulas, but they are all. Here it goes to infinity, really, on this scale. I mean, not literally infinity, but on this scale it goes to infinity. Here the loss is unbounded. Okay, so I want to describe a little bit more, the general picture here, and then connect, this toy model. Actually, this toy model, I think, also gives all the intuition for the neural tangent theory, right? Okay, so this is a long thing, but I'll first start by, giving a general, I start with some example of linear regression, how this connect with other things, then I give a general formula, again, in the linear or ridge regression case, and then derive some phenomenon and then match back to the neural tangent theory. And finally, I'll conclude describing what are the limitations of this theory. I mean, it has a lot of insights, but it has some important limitations. Okay, so we'll think of linear regression for a moment. So ridge regression, so we have covariates and responses, covariates as the feature vector zi's and responses yi's. And the zi's you should think of as the zi's of my toy example. So really the features, the w times xi, not the latent ones. And the distribution will be beta times zi plus noise, and noise is variance tau square. Okay, so one important thing here is that, as you see, I'll allow myself to use p equal to infinity. So what does it mean? P equal to infinity means that zi's belong to an Hilbert space. As you see, this makes perfect sense, and actually it's useful to think about that. Okay, so I want to look at the ridge regression, which minimize least square plus the penalty. The z is the design matrix, and lambda going to 0 plus is the mean norm interpolation, of course. So when lambda goes to 0, if n is less than p, then you will get a model that interpolates the data. So it's 0 training error. Of course, this is completely explicit and it's convenient to think about it in this, the formula. You can write it in two ways. This is the kernel trick. And I think this is particularly interesting because it brings out this n by n matrix that is the matrix, the gram matrix of the z or the kernel matrix. And this, of course, play a very important role in everything in the analysis, right? And then we are interested in test error and, okay, or better than the test error with respect to square loss, so the error on an unseen data. It's convenient to look at the test error minus the base error. The base error in this model is just tau square. And if you do this subtraction, you get just that this test error is just the error, the L2 error between beta hat and beta, but is the L2 error computed with the norm weighted by sigma, where sigma is the covariance of the z. This is very important if you think that, in particular, as in the exam, in my first example, sigma is very anisotropic, so it has some big eigenvectors and some smaller, big eigenvalues, small eigenvalues. So it's important to get beta hat right in the important directions and not in the other ones. All right. Now, just to so of course, linear regression is a very it's the first model that you probably teach to anybody. First, multivariate models, but actually is extremely rich, right? So I think about a series of kind of increasing complexity way of describing it, but actually they are all equivalent. So the first one is, okay, what I call well-concentrated covariates here because of mathematical reasons. But this is the first type of result that I'll talk about. In this case, you can think of the zi as sigma 1/2 times, okay, these xi's are not the same xi's as before, times some xi's. This you can always do. Xi's are isotropic, and simply assume some property of the xi's, right? And for doing the math, the typical properties that you want is the real properties that you want for doing the math. And I'll come back to this, is that this xi satisfy concentration of quadratic forms, right? So xi transpose times a matrix times xi should concentrate around its expectation that the trace of A. Right? So when you have this, then you can prove theorems. And there are many ways of guarantees this. For instance, if you want to get exponential tail bound, you can do it, for instance, by assuming that these xi's are log Sobolev, or even weaker, that satisfy W2 entropy transportation inequality. Okay, example number 2. Kernel ridge regression. In this case, the xi's are just come from some probability distribution in RD. Yi are a generic function of the xi's, and this function belongs to H, where H is a reproducing kernel Hilbert space for some kernel K. Okay, and you do ridge regression simply by penalizing, fitting, minimizing overall functions, and penalizing by the square norm in this RKHS, right? And of course, the function, because of this penalization, must belong to H. So now this at first sight is much more complicated than the example that I gave you before, but in reality is just completely equivalent. Why? Because an equivalent way to think about it is the following. You have a featurization map that maps RD into another Hilbert space. It's not necessarily H, okay? And then you minimize, you compute, you look at all functions that are linear in this phi of x, okay? And now my data are just the phi applied to xi's, and I do just plain ridge regression in this coefficient space beta, okay? And now it turns out that if you construct the feature map and the Hilbert space here in such a way that the gram matrix of the feature vectors is exactly my kernel, this guy is exactly the RKHS solution as before. Okay, so kernel ridge regression is just ridge regression, except that you're doing ridge regression with respect to these feature vectors that can be infinitely dimensional, right? So once I allow myself to look at p equal to infinity, I can cover this case. Now, the only difference is that one must be careful about the concentration properties, and this feature vector might not satisfy the same concentration property that I assumed in the first slide, but that is a technical thing if you want to write proofs. Third example, random feature regression. I mentioned this yesterday. Here I have again yi equal f star of xi plus epsilon. So as in the last example, the xi come from a probability distribution. And now what I fit is a two-layer neural network, but I fix the random first layer. Okay, I fix the first layer to be random. Okay, and I will only fit the B's, and the B's you fit it by ridge regression. Okay, so this is an idea that in some sense dates back to Radford Neal, and then was very much revived by Balkan, Bloom, and Vempala, and then especially this paper or Rahimi Recht. The way they really think about this in these papers is as a randomized approximation to kernel ridge regression, right? Now I want to think of it as, again, a toy model for neural networks in the linear regime. And of course, in the case of kernel ridge regression, I first described the kernel view. Okay, did I write it? No. Okay, I don't have the kernel view here. So, but this you can write exactly in the same form as in my first slide if I think of the Zi as obtained by applying this featurization map to the xi's, and the featurization map is simply the computation that is done by the first layer of the network, right? All right, so the three examples really differ only in the featurization map.
Sorry, I have a question about the
Is there any benefit in terms of, in reality, you should learn them, and perhaps in the next slide you see why. It's at the time at the time this was introduced in this paper was like they came from the kernel method viewpoint. They wanted a randomized method that is efficient and doesn't have the bottleneck, the n squared bottlenecks that comes. So their idea was I use capital N much smaller than little case n, and therefore I can fit it very efficiently, right? But no, here is really a toy model, basically, right? The real model that we are more interested in is the neural tangent model that I obtained by taking a 2 layers neural network and linearizing it around initialization. So this is an idea, again, that dates back to this paper of Jacob Gabriel Ongler, and then was studied in many other papers. And here I'm adding a parameter, a large parameter alpha, to show that now if I do Taylor expansion in this alpha, in 1 over alpha, the order 0 term is a coefficient times the gradient of my model with respect to the parameter. Okay, so this is the neural tangent model. And this is exactly the form that I've been talking about so far, that is a coefficient of parameters times a feature vector. Okay, and here I take the 2 layer neural network, and I remind you the computation that I did yesterday. If I do the Taylor expansion of this to first order, I get a term that comes from expanding the WJs, and the term that is this term, and the term that comes from Taylor expanding the EJs. Okay. Does this make sense to everybody? Okay. As I mentioned yesterday, this is far fewer parameters. So typically in this paper, we call the neural tangent model just this, right? One interesting fact, like one reason why, okay, if I have to use a linearized model, I think the neural tangent model is a more interesting model to use because it has this interesting property. It has many more parameters. It has n times d parameters, right? So it has more expressivity, a constant number of neurons, but it can be evaluated in the same time as this, right? Because it's exactly, the computation to evaluate this is basically 1 matrix vector multiplication, and this is 2 matrix vector multiplications, basically, right? So, or 1 matrix vector, and then, this you can pre-compute. Okay, so this again, we can rewrite in our kind of general way is, a featurization map applied to the xi, and the featurization map is this one. Okay, simply taking each xi, repeating it capital N times, and each time multiplying it by the derivative of the activation function multiplied by different right?
So excuse me, I have a question.
Sorry.
Yeah, I have a question about the concentration property that you explained. The concentration property, it seems to me some assumption that the xi are generic. I'm just wondering if in the empirical examples that you showed, like MNIST and so on, whether that assumption is reasonably satisfied, because that data might be coming from a very low dimensional or very special subset of all possible data.
Well, that has to do there are a few things, right? One is, what interests me is that phi of xi satisfies the concentration property. Second thing is, it's very difficult if you have a finite data set, to check whether it satisfies concentration or not, right? If you have a finite data set, the empirical distribution by itself will not be, for instance, sub-Gaussian, let alone log Sobolev, right? So, the reality is that is very difficult to check on a real data set. Now, it might be that it's easier to check the concentration of quadratic forms or to do some intermediate checks about the theory. If you fit these linear models, what I have seen is that, if you fit these random features or neural tangent models, the predictions of this theory are not too bad even for real data sets. But they become very different if you start feature learning.
I see. Okay, thank you.
This sort of a class of function have finite Rademacher complexity?
Well, the Rademacher complexity, you know, this is a class of functions that are linear functions, right? I mean, they are linearly parametrized function in this thing. So it's the same Rademacher. So you could think of this as just B times Z I, right? B times, so this is the function where Z is the featurization map, but the featurization map doesn't have any parameter, right? Z is phi of X. So the featurization map doesn't have any parameter. So if this is less than R, you know, the Rademacher and, you know, B is less than, you know, whatever, gamma, the Rademacher complexity, or what I call the rho, the Rademacher complexity in this class will be rho R divided by square root of n. But we'll be interested in fitting to interpolation these things. So, you know, we'll take a norm of B that is larger than what it should be. Okay, so the connection with neural network, I described the heuristics of this. You know, you do linear expansion around initialization, and you know, the idea that this converges very quickly to an interpolator. So let me state one theorem that makes this connection a little bit rigorous. Okay, and for convenient, I will use a special initialization here. I'll initialize my neural network like this. I'll have a parameter gamma here over square root of n, and then I'll take you know, the first, let's say, the second layer weights to be, you know, half of them equal to +1 and half of them to be -1, and then the WJ, half of them to be random and half of them copying the first half. This initialization is convenient for this kind of theorems, and the reason why it's convenient is that f at initialization is exactly 0. So this is, if you want, a particularly complicated way to encode the 0 function. Okay, so assume that the network is initialized like this. Results look a little bit less pretty if you initialize it completely random. But assume that is initialized like this, then, okay, this is really a paper of Oimak and Sultan Oktabi. If the number of parameters is bigger than d log d, and, you know, the square root of sample size squared divided by number of parameter is less than gamma, then the following happens. Gradient flow converges exponentially fast to a global minimizer, to an interpolator. So in particular, this proved that there exists at least an interpolator, right? And in fact, there is many of them, because two random initialization will converge to two different of them. And okay, you can compute the rate of this convergence. This is a constant, this C is a universal constant, and this is the way it depends on gamma, D, and N. And further, the neural tangent model is a good approximation for the true model for all time. That is, for all time, if I look at the difference between these two models, so I look at this as two functions. I look at the difference between these two in L2. In L2 because I'm looking at square loss, so this controls the difference between the test error. This is upper bounded by something that is basically small when the ratio between these two sides become large, okay? So in particular, one thing to observe here that, okay, here it will be much prettier if you had, and it should be the case, that there is lowercase n over uppercase n times d. You know, the overparametrization ratio should appear here. But I think this is a weakness of this theorem. I suspect it's an artifact of the proof that the square appears. But nevertheless, this says that if I take the scaling in front of f large enough, as long as you have some overparametrization, okay, here there is a log factor, but as long as you have some overparametrization, you will find that zero training error, and the neural tangent model will be good. Okay? So there is always a way to train your neural network so that you achieve zero training error and you're essentially fitting a linear model. And this is Shizaimbach introduced the term of lazy training, meaning that this is the lazy way of making your neural network training converge. You just scale the weights up and overparameterize. Okay, so that's the formal connection, and now we are justified to look at this linear model, and I'll start from my first model, just linear regression, where Zi are in a Hilbert space, and let me list the assumptions here, or some of the, not all of the assumptions, the most important. Sigma will have finite rays. This ensures that the Zi are finite norm, and let's say the largest eigenvalue is 1. This is without loss of generality. There is this condition. This basically, if you think about it, means that beta mostly is concentrated on the eigenvectors with large eigenvalue of sigma. So this is the alignment, right? Because you can think of this as saying that sum over I, 1 over lambda I of sigma, beta times bi square, where these are the eigenvalue less than infinity, the eigenvectors less than infinity. Okay, so this is basically concentration. Then there is these assumptions that basically defines this parameter, the effective dimension. Okay, I don't know if effective dimension is a good name for this, but this is basically the ratio between all the eigenvalues after the kth one and the kth eigenvalue. These are the eigenvalues of sigma, sorry. Okay, so why is this a dimension? Because if I think that all the eigenvalues after the kth one are all equal to the kth one, this is basically how many eigenvector you have after the k eigenvalues. So this is the dimension of the rest of the space. And then finally is the concentration, and here we look for exponential, perhaps. So for this is sufficient that concentration of one Lipschitz convex function. For instance, what is the sigma? The sigma is it's any constant such that this is true for every k. I will define it again. I will copy it again. Okay, so under this condition, this is the form of the theorem. If you look at the test error, and if you look, this is given by the test error of a simple model that we call the sequence model times a multiplicative error term. And this is 1 plus something small. And this is small under certain conditions. And I will fill in the detail. I have to fill to the detail here. What is this and what is this, right? The important, a couple of remarks here. Here we approximate the test error, the real random test error by some prediction with the multiplicative factors, which is nice because this will allow us to say something also when this error goes to 0, no? or this error goes to 0. It turns out that basically all the examples that I can give before, random features, kernel ridge regression, neural tangent model, at least all that have been proved can be derived as special cases of this formula if you just plug in, as you see, the covariance, etc. So all of these can be derived as special case. Now, in some cases, the assumptions are not verified. And so because of that, that required historically, a few years ago, different proofs, but one could just try to strengthen this theorem. And in fact, it has been done in some cases. And okay, so finally I have to tell you what is this risk. Okay, so I'll tell you what is the sequence model equivalent. This is a very simple interpretation. And the key parameters is this lambda star. And the way to think about this is that this is an effective regularization. Okay, so you put in a regularization lambda, but what turns out to be the case is that the model is as if it was regularized with lambda star. And lambda star is the unique solution of this equation. Okay, so if you think about this equation, the left-hand side the right-hand side is a function that is decreasing, starts at whatever it's p, and it's a function that is decreasing with lambda star. And the left-hand side, so this is, and the left-hand side is a function that is increasing. And so there is a unique solution. This is what I call lambda star. Okay. Now, one interesting fact, one important fact is that if you trust me that is an effective regularization, one interesting fact is that this is a non-zero limit when lambda goes to 0, because lambda goes to 0 means that you're solving this equal n, and this has a finite value, a non-zero value, even when, as long as p is bigger than n, even when lambda equals 0. Now, you'll see in a minute why this is important. Okay. Okay. You'll see in a few slides why this is important. All right, so this defines this lambda star, and the error term depends on this lambda star, and I will not write all the details, but depends on this d sigma that I rewrote here, right? So this is, and depends on this chi. Chi is the ratio of this, here kappa and eta are two constants, and so forget the, typically lambda star is of order, lambda star at 0 is order of the eigenvalue of order n for some constant, the nth eigenvalue of this covariance matrix. So morally, this chi n is something that is like d sigma eta n divided by sigma cn times d sigma time divided by n. Okay, and for instance, if you have power law behavior of the sigmas, this is a constant. So this is chi is the effective dimension divided by n. And for the error term to be small, the key or one of the key conditions is that you need chi to be less than n to the 1/3, which boils down to the effective dimension to be less than n to the -4/3. And this is verified in a lot of examples.
Sir, could you explain once what is the sequence model equivalent?
Sorry?
Sequence model equivalent that was there in the previous slide.
Sorry?
Sequence model equivalent.
The sequence model equivalent, I didn't yet introduce it. So far, I introduced just lambda star. This is the solution of the equation. And it will come in a couple of slides also. Okay, so now these are key assumptions. I will not list all the assumptions because it takes a couple of pages, really. We try to write this in a more general way possible. And now what is the equivalent model is the following model. You want to estimate, instead of beta, the projection of beta on the eigenvector of sigma, right? This is equivalent, so call this theta I. And now instead of y, I observe ys, where ysi is the ith eigenvalue times theta I plus Gaussian noise. So these are IAD Gaussian. So this is what in statistics people call a sequence model, namely you have a sequence of unknown coefficient and you observe them separately in Gaussian noise, right? And there is this twist here is that there is this eigenvalue multiplied them. Right? So there is no X, no Z matrix, no random design matrix. There is only this sigma. And then I estimate each of them independently using ridge regression, one-dimensional ridge regression with the regularization parameter lambda star. So this is why you call this the regularization parameter. So this is a very simple statistical model. It's just a bunch of independent Gaussian estimation that you're solving by each of them by some linear, or by some linear thing, linear estimator. Now there are two objects here. Of course, there is lambda star, and then there is this noise level omega. Omega, you choose it to be given to be the solution of this equation that you can solve explicitly, but it's given by some formula. It's not important. And now the claim is that, or the definition of RS is just the prediction error, or the test error in the equivalence sequence model. So this theorem is saying, take your matrix, you want to fit this y equals z beta plus noise. And the difficult part is that this z is non-diagonal and it's random. And what I'm saying here is that this is equivalent to y equals this sigma times beta plus noise, where sigma is diagonal without loss of generality and non-random. And the only thing that you have to do to map one into the other is adjust the noise level and adjust the regularization parameters. And once you adjust the two indices, then the two error maps onto each other, and there are explicit formula. And now it's obvious that working with this guy, for instance, if sigma is the identity, this is just one line. In general, it's quite easy to derive tight formula for this. Okay, I'll give you two examples of this. One is power law decay of the eigenvalues, and the other is critical decay. Remember, we need the eigenvalues of sigma to be summable. So alpha is to be either bigger than 1, or here you need the log exponent to be bigger than 1. Okay, so what happens, and all of these examples are with lambda. So before going into this, let me mention that you see this lambda star plays the role of regularization, right? As I told you, is of order if lambda equals 0, is of order the nth eigenvalue, right? So basically this, what it's doing is keeping all the, shrinking to 0, all the components that are beyond nth 1, okay? And keeping, basically unchanged all the ones that are before the nth 1. There is a little bit more to it, but the basic intuition is more precise than that, but that is the rough intuition, which is what makes sense, right? You shrink all that is, that you can estimate, and then, so this is what the ridge regression with lambda equals 0 is doing in this case. It's basically shrinking to 0 all the components that corresponds to junk features. Okay, so this is power law decay and critical decay. Power law decay, so here we plot the bias, the variance, and the risk as a function of the sample size, and I don't remember here what is the dimension here is very large, so it's basically infinity.
Question.
And yeah.
The previous slide, can you please explain how we computed the effective noise level?
Well, the effective noise level is formally obtained by solving this equation, but you see, this can be completely written explicitly, right? Because, okay, I can do the calculation. This is sum over I sigma I, and then the expectation of what? Theta at I, S minus theta I square, right? And theta Si is equal to sigma I 1/2 over sigma I plus lambda star times YIS, which is whatever, it is sigma 1/2 I theta I plus omega over square root of n GI. Okay, so you plug this in here, and then it's one line. Now I don't remember the formula by heart, but it's some simple formula. And then you get an explicit, all of this is, so this will end up to be omega squared times a certain coefficient that depends on all the sigmas and on lambda star. So in reality, this is a linear equation for omega.
What is tau?
Tau is the noise, is my original noise. Okay, so you see it will be a linear equation, so you will get that omega is the original noise times some coefficient. And this formula gives you the coefficient.
From where did the n minus lambda by lambda star come from?
Sorry.
Yeah, from where did this term
This
come?
equation comes?
Yeah.
Well, this equation is, comes from the random matrix theory. I mean, okay, so I don't, do I have a one-line explanation of it?
I mean, the RHS looks like this estimator kind of, which is the equivalent sequence model.
Yeah, so all of this is, this is the error in the equivalent sequence model. I mean, both equations are non-trivial, right? Where do they come from? I come from, I don't have any better way than, so the way you prove this theorem is basically you write explicitly what is the risk. The risk is a certain, everything is explicit in ridge regression. So you can write beta hat in terms of the matrix Z and the real beta. You plug in, you get some expression, and this is, now you evaluate the asymptotics of this. So now this is like a matrix element of a resolvent of a random matrix. And now you do some random matrix theory to compute the asymptotics of this. Okay, so here you get this phenomenon where as you increase the sample size with power law decay, the bias decreases, as it should be, but the variance increases and goes to a plateau. So as a consequence, if you don't put regularization, this is for different value of the exponent, as if you don't put the regularization, this is non-consistent. So this is telling you that if the eigenvalue decay like a power law, you should put a regularization, because otherwise you will end up with not being consistent despite having infinite sample size. Okay. This is the case of critical decay, and here there is this interesting thing that both the bias and the variance go to zero. Basically, what happens in this case is that the effective dimension is larger because the degree of the eigenvalue is lower. That makes the lambda star be larger as a function of n. And so the effective regularization is larger. So even if you don't put a regularization by hand, that is sufficient to drive the variance to zero. And therefore, this is consistent. So you have a model that has highly overparameterized, has infinitely many parameters, finite n, you don't regularize, you're interpolating the data, and despite this, you are consistent, so you converge to test error equals zero. So this is what Peter Bartlett and collaborator called benign overfitting. So each of these plots, I have the bands are numerical simulations, and then there is a line, actually two lines in the middle that are the mean of the empirical results and the predictions of the theory, and they are undistinguishable. Okay, in this case they are undistinguishable also because they are very small, these figures. They are indistinguishable in general. Okay, so I mentioned this benign overfitting phenomenon. Bartlett and others, what they did is that they analyze ridge regression basically in the same setting, and they bounded the risk instead of computing the asymptotics. So they derived some clever bounds that demonstrate this kind of that are in some sense order optimal and demonstrate this benign overfitting phenomenon. I wanted to show that you can rederive these bounds simply by looking at my formulas, right? And here I rewrote the formulas. And I could do it, but perhaps I'll skip it because in the interest of time. But basically, this very much boils down to using the intuition that I described before. And the intuition is that what this formula or what this theory that I described is telling you is that you're estimating in an unbiased way, you're estimating very well the components that corresponds to large eigenvalues of sigma, and you're effectively shrinking to zero or close to zero those that correspond to small eigenvalues, okay? So you have to compute what is lambda star and when this transition happens. And if you do that a little bit carefully, you obtain these bounds just from our formula. You obtain a bound for the variance and a bound for the bias, and the bound for the variance depends on this k star, that is the first k over, the first k at which sigma k becomes smaller than lambda star, basically. So this is basically, okay, if you neglect this term, the variance is the number of eigenvalues that are larger than lambda star divided by n. Right? So this is telling you that this would be the variance of normal linear regression if I fit a model with only k star parameters, right? So it's telling you that the model, what it's doing is simply, there is this effective regularization, and the model is fitting all the parameters, doing linear regression on those parameters, and then there is an additional fudge term, and this term is the term that goes to zero or not, depending on what is the tail of the eigenvalues. If the tail of the eigenvalues is sufficiently small, this is what you get. This goes to zero also. Okay, I want to switch gear and go now to kernel ridge regression. Again, this is the setting, and I'll take a measure of the xi that is uniform to the sphere, generic function in L2 of this measure of the sphere, and an inner product kernel, since the measure is isotropic, with some genericity condition. And okay, many of these things can be generalized and abstracted away, and I do kernel ridge regression on this model. And here again, this result you can obtain by applying the general formula that I gave before. The way we proved it originally was different, but the result as stated here is very simple. It says that if the sample size is much bigger than d to the L and much smaller than d to the L plus 1, then for any regularization small enough, the risk of this kernel ridge regression is equal to the projection of f star onto polynomials of degree L plus 1 or larger, plus a small error term. So what is this saying? This is saying that kernel ridge regression is fitting exactly all components of the projection of f onto polynomial of degree L or smaller. Why this comes in, why this sandwich comes in, if you think about it, how many parameters do I need to fit a polynomial of degree L? Roughly d to the L, right? So this is saying that in this interval, I have enough data to fit all the coefficients of polynomial up to degree L. In theory, I could fit a little bit more if n is bad, but I'm not fitting anything of that. And the reason why I'm not able to fit anything of that is because, from the point of view of this kernel, all of those polynomials are completely equivalent. So either I fit all of them or I don't fit any of them, basically. So all of those are shrunk to zero. In other words, if you think about the kernel, so before we had this covariance matrix, right? And what mattered are eigenvalue of this covariance matrix. This corresponds to eigenvalues of the kernel, right? And if you do your analysis eigenvalue of the kernel, there will be one eigenvalue that is of order 1, and then these eigenvalues that are of order 1 over d, and then this square eigenvalue, roughly this square eigenvalue of order d square, and so on, right? And as I told you before, in case of linear regression, what happens is that you fit unbiased all the eigenvalues up until some threshold, and you shrink to zero all the components of smaller eigenvalues, right? And this is exactly what's happening here. The threshold is exactly fixed from what you would expect information theoretically, right? It's when you have enough data to fit well those guys. Okay. And interestingly, no inner product kernel method can do better. In particular, if I take lambda different from zero, I cannot do better than this. So this is another example in which basically, interpolation is optimal. Okay, there was related work about the same time with different kind of results, in the same spirit, though, by Sasha Racklin, Tengyuan Yang, and Alex Shai. Okay, one interesting thing is, what is the intuition? Why interpolation is optimal, right? One way to think about it is that we are fitting a function in a high dimension, and in general, fitting to noise data point is a bad idea, right? It's a bad idea. Why? Because when the test sample happens to be close to the training sample, you will predict close to the train sample, right? So if you have a function and then you have noisy data, in general, it's a bad idea to fit like this. Why? Because when a test sample happens to be close to the train sample, you will predict away from the true function, right? So this is a bad thing to do in general, but in high dimension is actually not so bad, because every new data point, every test point will be with high probability basically orthogonal to all the trained data points, right? Right? So even if you interpolate, this creates small spikes in your function that do not really matter. Right? So this is a cartoon of what is the train error as a function of log sample size over log t. All right. Actually, so since we did this work, people were able. This was a cartoon, and we couldn't figure out in that work what happens exactly at this threshold. But this was eventually, the precise behavior was actually proved in a sequence of papers, in particular by my former student Theo Misiakiewicz and my current student Basil Said. In particular, Theo and Basil, they basically extended the general framework that I presented at the beginning. So they have an extension of my master theorem that then allows them to nail this example. Okay, I'll skip random features because I showed this figure before, and I'll state one theorem about the neural tangent model finally. So again, this is the featurization map, and you're fitting linear regression with respect, ridge regression with respect to this featurization map. This is the model. Okay, there is an equivalent way to think about it is the function space view, right? You can always say that you are fitting a function and penalizing by an RKHS norm, and in this case, as always, the right norm to put is the RKHS norm corresponding to the kernel that is obtained by taking the inner product of two feature vectors, right? If you think about your feature vectors before, if you take the inner product of two of these at 2 points, you get exactly this kernel. Now, this kernel, it's an interesting kernel, is a random kernel, right? Because this point wi, these weights wi are random. But if you compute its expectation has a nice structure. So there will be x1, x2, And then all, the sum is of n terms that are IID. So you get 1 over d, and then expectation of sigma of W transpose X1, sigma of W transpose X2, and the expectation is over W. And remember then I'm taking W uniform on the sphere or something like this. So this must be a function of all invariant of X1, X2. So this will be the inner product of X1, X2, and then the norms of X1 and X2. If I take X1 and X2 on the sphere, so this will be overall a function of X1, X2 over D. Okay, so in expectation, the kernel is the same as the kernel, as the same structure as the kernel of the result that I showed before. Okay, I'll skip this, perhaps. So what you want to show is, want to show that you recover basically kernel ridge regression with respect to this expected kernel. And this is an example of a simulation where on the x-axis I have log of the number of parameters, on the y-axis I have the test error, and the dashed line the kernel ridge regression with respect to this expected kernel, and the continuous lines are just finite width neural tangent models. Right? And so you see this spike at the interpolation threshold. This is the interpolation threshold. And then this quickly converges to the limit. So formally, these dashed line are the limit n to infinity, but actually this limit happens to appear to happen very early. So this tells you precisely what should be the asymptotics of this curve that is kind of the most important part of this curve. And in fact, this is the theorem that we proved with the Chao Zhang. We proved that the risk of finite width kernel, finite width neural tangent model is the risk of the corresponding kernel ridge regression model. This is the test error, plus something that becomes small as soon as the overparameterization ratio becomes, number of parameters becomes much larger. So this in particular inherits all the phenomena of this benign overfitting. In particular, in this regime, this risk will be the risk of perfectly fitting the first degree L polynomial, and in particular, you'll get that lambda equals 0 will be nearly optimal. Okay, so at least three insights. The risk will be equal to the limit when you are overparameterized. Overparameterization, you can keep adding. You can keep adding parameters to your model, and this will not hurt. And interpolation will be nearly optimal, at least in some cases, when this happens for kernel ridge regression. Okay. Well, the last thing I want to talk about is what are the limitations of this linear theory. So this linear theory is very interesting. I mean, one thing that, by the way, is very nice about it is that, okay, here we worked out, and there is, follow-up works on this simple 2 layers neural network, but you can take, any deep learning model and then, try to repeat this, right? It boils down to, constructing the right featurization map that's associated to this model, and then, analyze property of the resulting random matrix, right? And this allows you to think about generalization error and so forth. For instance, one case that we looked at back then was, models that are invariant, some simple CNN models, right? There is some work on 2 hidden layers fully connected networks, but the picture is not clear. There is some work about neural tangent getting sharp results, but also there the picture is not yet complete. So you can take your favorite model and your neural network model and analyze it always in this regime. Okay. Now, what is that is not good about this kind of theory that you can construct for any model. I give you the simplest example that demonstrates this. The simplest example, I take special case of this, of my single index model. By the way, all the results before, the function f star needs not to be a k-index model. The function f star is a generic L2 function. Right? Doesn't need to have a low-dimensional structure. Because after all of these methods don't exploit the low-dimensional structure. Now let's take something that has a low-dimensional structure, is a index in the model, and the nonlinearity is actually the same as my activation function in the network. And I fit a model with, okay, again, the standard initialization, and let's say that I initialize it randomly as I was doing before. Now, what do we know about this thing now? We can think about the simplest possible case is the case of only one neuron. Right? So in this case, my function is just a function of W, has two parameters, W the vector, and then this A, first coefficient. Oh, sorry, gamma is 1, I set it to 1. Okay, so there should not be gamma here. So I'm minimizing this over W. And let's say that I minimize it by gradient flow. Okay. All right, so this is something that we did, okay, there are various versions of this result. I mentioned one from a paper of ours that was 2018. If I say A, set A equal, there is no gamma, sorry, I erased it from the slide. A equal 1 fixed. I have some assumption of sigma. It has 3 times differentiable, strictly increasing with bounded derivatives. Then if the sample size is bigger than d log d, gradient flow converges to the, a unique optimum, converges exponentially fast. And this unique optimum has small generalization error. The optimum error that you could hope for is d over n, right? You have d parameters. If you do, standard bounds, you get d over n for the optimum error. Just by this simple landscape analysis, I get d log n over n. I think, the log n was just an artifact of the proof in this paper. It's not very important. Okay? So this model, in other words, under these assumptions, it's very easy to learn optimally. You need only d samples. Does this make sense? Yeah. This works for any initialization. Now, if you take an initialization with unbounded norm, let's say any initialization with bounded norm, and the C0 will enter in the. Okay, so this is for gradient flow, but you can prove something similar for gradient descent. It's just showing that basically the population risk behave very nicely, similar, a toy version of what was shown in the talk this morning, and then showing that the empirical risk is very nicely concentrated around the population risk, both at the level of value and the level of gradient and Hessian. Now, if I instead apply the theory that I talked about in this lecture, what do I obtain? Well, if the number of neurons is large enough, and we said it has to be, in the model has to be yeah, here I made a mistake. So this should be nd bigger than n log n, and n bigger than, capital N bigger than n square over d. Okay. So this is, I copied the bound and I reversed the bounds that I had about my theorem for approximation by the neural tangent model. But in passing terms from one side to the other, I changed the letters randomly. So that should be, if I remember correctly, should be nd bigger than n log n, and n bigger than n square over d. Okay. In other words, if it is sufficiently, your network is sufficiently big, then, so if number of neurons is large enough, then gradient flow converges to zero risk exponentially fast. The risk of the model is very well predicted by the risk of the neural tangent. And the part in the last part of the talk, the risk of the neural tangent will be if n is between d to the L and d to the L plus 1, will be the projection of sigma onto polynomial of degree bigger than L. Remember, this should be the projection of f, but if you compute, f here is sigma of w star times x. If you do your harmonic analysis, you get that this is the same as the projection of sigma onto polynomial bigger than L in L2 of the Gaussian measure. All right. So what this says, it says that even the sample size is d to the 10, the error is bounded away from 0. So in other words, this is, we know two things, right? That if you do a network with, if you train a network with one neuron, it's sufficient that the sample size is d, and you achieve very small test error. If you train a network with many, many neurons, any polynomial sample size, you will have an error bounded away from 0. Okay? So this seems to say that, so this is in picture, what happens as the width of the network increases, the test error goes from almost 0 to something very large. And this is not a bound. This is an equality up to epsilon. So this is a fact. As you take the network larger and larger, things fail. And despite this, we keep saying that large networks are good.
This is the result on gradient descent or
this is gradient descent. Both results are on gradient descent, right? Because gradient descent or gradient flow enters here. This is a result about gradient flow converges to minimum. And this is about gradient flow being well approximated by gradient flow is in the neural tangent model, and the model being well approximated by the neural tangent model, right? So both results about gradient descent from random initialization for this model with different width.
How do we reconcile this with the fact that overparametrization works well in general?
Okay, so this is the next lecture. Okay, so this is a paradox a little bit. So the question is, you increase thing. I don't know rigorously what happens in between, but doesn't matter too much, right? This is saying that we are doing something wrong, right? Because if I use a bigger model, I said this is a very basic question you can ask. Does a more complex model always work better? And in this case, we have a case in which we are not able to make it work well. So there must be a way to make it work better.
One possibility is the NTK regime is not the right regime to be looking at least.
But this is what's happening. Now you might argue that in between these two there is a dip, right? Or this is flat for a long time and goes up, no? But I don't think Actually, I have strong reasons. I don't have a proof that, it could be, I don't know what happens in between these two. It could be that this stays very small and then goes up, right? But here, this is a curve. There is nothing, barring that case, there is no regime, right? Okay, so either we are doing something, either this is the end of the story, or we are doing something wrong in how we are training our network, right? Okay, I will keep the suspense for tomorrow. Yeah, this is why we kept working on this ridiculously simple model. Okay, but the conclusion is that, okay, linear models I think still are very interesting because In some cases, there is evidence that they are not a bad approximation, right? Empirical evidence. And it's a general theory, and it explains why interpolating can be optimal at high SNR. And I think from a technical point of view, I think, okay, there have been a lot of steps towards, many of these results were, as I said, proved on a case-by-case basis, but now we have a kind of general tools to prove them, in a unified framework. Okay, that's all. Thank you.
Questions if we have any.
Yeah, so I just want to be sure about the last puzzling thing you showed. Just wanted to make sure I understood it right. So you said there's a single neuron that's the actual model, right? That gives the label. You have an overparametrized network that you're fitting, but you're not linearizing the network or anything, right? Like there is feature learning happening through the gradient flow, and you're still saying that when n is
I don't know what happens, right? I mean, okay, should I just say the following. Take data generated with this model, right?
Right.
And then I fit this model.
I see. Okay.
With initialization that I described before my theorem. So basically initialization so that the function, that doesn't matter in reality. You can do it, if you take capital N big enough, think that you take AJ IID of order 1, IID Gaussian, and the WJ again, IID Gaussian. The standard Lican or the standard Xavier initialization.
Sure.
And then run gradient descent.
On both A and W, right? Just to
on both A and W, or only on W, whatever you like better, right? And I claim that my theorem before from Oimak, Sultan Kutabi, etc., and some refinement implies that this formula is completely wrong. But if you use the corrected formula, if capital N is above a certain threshold, this will be very well approximated by the neural tangent model.
Nice.
And the neural tangent model will be, N is big enough, very well approximated by kernel ridge regression with respect to rotational invariant kernel. And therefore, the final test error minus the base test error will be just the projection of sigma onto whatever polynomials of degree bigger than n. Okay, so if you take sigma that is not a finite degree polynomial, this will be bounded away from 0 for any polynomial sample size.
Right. Okay.
In contrast, in the same model, I fit the model that I should fit, that I would fit is if I knew sigma, if I knew the correct data distribution, and then gradient descent will converge well and will achieve basically parametric rate. Okay. So now where does this come from? That is a little bit the puzzle that I'm posing to you, and the puzzle that made me not stay awake at night, but think for several months. But now I think I have a clear idea of what's happening.
So, okay, let's thank.
I understand everybody wants to run lunch. Me too.
So I have like a small question. So are there settings where people actually use overparametrized linear regression?
Overparametrized linear regression. Well, yeah, I mean, often you have few samples and then you add, you use more features than sample, right? I mean, n less than p, this is, very common in statistics, in modern statistics, right? Now, one way to approach this is very different from this. It's not ridge regularization, is using L1 regularization. So the reason why that works is very different than the reason why this works. Now, L1 regularization is very good at kind of selecting a parsimonious model, a small model, and so it's a model that is interpretable. So if you want to estimate the parameters and have an interpretation, it's probably the right thing to do. But I've seen examples in which also in kind of, statistics applications, people used ridge regularization, and it actually, with respect to test error, it works well, competitive with L1 or sometimes better. So I've seen papers like that. Miller was doing something like this. So yeah, n less than p is very common in high dimensional statistics, and whether you want to use sparsity or not depends a little bit on what is your objective.